Chapter 6, Network Hardware. Identify the functions of LAN connectivity hardware. So we're going to talk about the hub and the switch and the router and some of the specific ways that those devices work. We'll talk about installing, configuring, and differentiating between network devices such as NICs, hubs, bridges, switches, routers, and gateways. And that, for the most part, tends to go from easiest to most complex. It's not exactly true, but for the most part, that's kind of how it advances. Explain the advanced features of a switch and understand popular switching techniques, including virtual LAN and VLAN management. So we'll talk a little bit about that. I'm going to skip over some of that, but we'll talk a little bit about it just to kind of get an idea of what that is. As far as explaining the advanced features of a switch and what they're talking about when we get there is this idea that switches operate at multiple or different layers. And it depends on how much of a purist you want to be as to whether or not you can have a layer 3 switch, or whether or not that's just a different name for a router. We'll talk about that a little bit more when we get there, but for the most part, it's a router. Explain the purpose and properties of routing and describe common IP version 4 and IP version 6 routing protocols. So we'll talk about some of the common routing protocols that exist. Just kind of talk about some of the different the distinctions between them. So network interface cards, or NIC, that's the physical part of the computer that allows you to put the ones and zeros onto whatever medium you're using, whether it's copper or fiber or radio, for that matter. So it acts as a transceiver. It both transmits signals as well as receives signals. It operates at the physical layer and the data link layer to issue those data signals. It allows you to assemble and disassemble data frames depending on whether or not you're sending or receiving. Allows you to interpret physical addressing information, and it determines whether or not you have the right to transmit data on that particular network. So NICs can potentially have what they refer to as being, be referred to as being smart. That's not always the case. Some basic NICs are just going to do what they're supposed to do. But if you end up getting a higher dollar NIC, you can in some cases do packet prioritization, so you can do some of the advanced management functions potentially. Network management, so it provides information back to some central location that says this is how much data that's going through this NIC, this is how many collisions that have been detected, this is, so you can start to get information about the performance of that particular NIC. That's useful in the future if the NIC starts to exhibit some kind of a problem. You can potentially determine that that NIC is failing before it's actually failed, send somebody out to replace it before the user is really aware that there's a problem. You can potentially do buffering, traffic filtering, etc. So those are some of the advanced features that a NIC might have. Does not analyze information. What they're talking about is it operates at layer 1 and layer 2. All it's doing is opening up the packet or opening up the frame and looking at the MAC address to see if it's at the right. It's comparing it to the destination MAC address if it's being sent to that particular computer. If it matches the destination address to its own physical address, then it's at the right location. Other than that, it's not doing anything with respect to any of the layers that are above it. It doesn't care about the IP address. It doesn't care about the application layer address. It's not doing any analysis on that type of stuff. So the NIC is just operating at layer 2, layer 1 and 2. As far as importance, they talk about it being common to every networking device. You've got to have some kind of NIC for every device that connects to your network, whether it's wireless or wired, it doesn't matter. There's got to be some type of a network interface connection to be able to connect to the network. Types of NICs, there's several different types, but as far as some of what they're dependent on the access method, the network transmission speed, connector interface. So are we operating token ring? Are we operating via Ethernet or some other type of protocol? Transmission speed, 10 meg, 100 meg, gigabit, etc. Connector interfaces. Are we using BNC connectors? Are we using RJ45 connectors or some other type of connector? Compatible motherboard or device type. In other words, can we plug it in? Is it a PCI Express card, a PCI card, ISA card, etc.? And then manufacturers. So those are some of the things that we want to know about when we're trying to select a NIC device. If it's an internal NIC, we've got it, well, regardless of the type of NIC, we've got to connect it somehow to the bus of the system. And if we're talking about an internal bus, it's well, any type of bus is a signaling pathway. Think of a bus as kind of like your highway. You can have a highway that's 2 lanes, you can have a highway that's 8 lanes. In West Texas, you can have a highway that's 16 lanes. So that determines the speed or how much data you can send down that highway. The speed limit is how fast you can do it. Those two together tell you how much data, how much throughput you really got. That's our bus. That's an equivalent of a bus. A data bus is doing the exact same thing. How much data can it send down that data bus? Motherboard uses a bus to transmit data to the computer's components, such as memory, processor, hard drive, and the NIC. It differs according to capacity, such as the width and the speed, which is what we were just talking about. And it does so in parallel. It transmits the data in parallel. Now, the way we interface a NIC with a data bus is through the use of expansion slots. If our computer has expansion slots, we can plug in an expansion card into one of those expansion slots, which gives us additional functionality, whether it's a network interface card, a sound card, a modem, whatever it is that we decide to use. That's the purpose of a bus, is to allow us to be able to add those additional peripherals. So an expansion card gets plugged into an expansion slot. Expansion card, a circuit board for additional devices, all the stuff that I just got through talking about. Now, those buses are different types, like I was just talking about. We could 2 lanes, 8 lanes, 16 lanes. We've got several different bus types. The most common in use right now is probably a PCI bus, PCI or PCI Express. Probably the most common bus types that you see. PCI, peripheral component interconnect, is either 32-bit or 64-bit wide. And it's got, depending on the specific one, you've got different clock speeds as well. So how wide is your highway and how fast is your highway? What's your speed limit? So that gives you a maximum data transfer rate of 1 gigabit per second, which is pretty good. It's been around as a standard for quite some time, but it's gone through various iterations. The last one, version 3.0, 2004, as far as PCI itself. So a PCI card might look something like that, and what you really probably want to focus on is the connectors right down here, the part that actually slides into the expansion slot, because that's what really kind of tells you what type of card that it is. They tend to be keyed, which is what this little slot is right here. It's kind of hard to see, I'm sure. So you got a slot here. They're keyed. It makes it very hard, if you're paying attention, to plug it into an incorrect slot. So that's a good thing. So pay attention to things like that. Other types of buses, you've got ISA, which is one of the original expansion standards. Been around a very long time. It's really pretty slow, so you don't really see those on anything anymore. But it is something that was kind of the beginning of it all. You had an extended ISA that came out after that, EISA, which was a little bit better. I believe they were all 16-bit and a faster bus speed. But PCI is really the standard anymore. One of the big advantages to PCI, not only its speed, but it's also compatible with Macintoshes. What does that mean for if you're a peripheral maker, to somebody that makes expansion cards? That means you make one card, you've got 2 markets for it. So they can produce more of the same thing without having to produce this one for PC and this one for Mac. Makes it a little easier on them. PCI Express, 32 or 64-bit bus, maximum 133 megahertz clock speed, transfer rate of 500 megabits per second with full duplex transmission. Advantages of PCI over PCI Express over PCI: more efficient data transfer, quality of service distinctions, which is what we've been talking about, so you should all be familiar with that. Error reporting and handling, and it's compatible with PCI compatible software. So as far as drivers and stuff like that, a lot of that stuff it does not have to be rewritten. PCIe slots differ from conventional PCI slots, so you can't. There's a separate slot for PCI Express, and it varies by lane supported. Lane offers full duplex throughput of 500 megabits per second up to 16 lanes. So at 16 lanes, you can get up to 8 gigabits per second throughput. So here's an example of a motherboard. We might have an old ISA slot there, a couple of PCI slots, PCI times 1 times 16. They're distinctive slots. So again, if you pay attention to your expansion cards and your slots, you're not going to have any problem plugging the wrong one into the wrong slot. As far as determining your bus type, read documentation. They're going to send you a book with your computer, with your motherboard that you end up getting. Throw it away because it's out of date when you got it. Look it up on the internet. Pull it up on the internet. It's going to tell you exactly the specifications for that motherboard, and you're going to know what your expansion slots are. Once you do it long enough, you can look at them and identify them just by looking at them because they are distinctive. Any questions so far? Peripheral bus standards. Attach peripheral devices externally. Obviously, that's a lot easier. You don't have to pop the case or anything like that. Sometimes it doesn't necessarily look as clean, but it's certainly easier to do time-wise. It's more convenient if you're on the go and those types of things. So simple installation. On laptops, you've got PCMCIA slots, standards for externally attached cards, including things like external sound cards, network cards, etc. Basically, it's just a little card that looks like, it's a little bit bigger than a credit card is what it basically looks like. Originally a 16-bit interface running at 8 megahertz, so relatively slow. So you see something like that, it just slides into a slot, a PCMCIA slot on a laptop. Started back in the 90s, a card bus standard back in the 90s with a 32-bit interface, running a little bit faster. Matches the PCI expansion port standard. It was a way to kind of do the same thing that you have for standard PCs or desktop computers. Allow laptops to be able to have expansion cards in them, and that's what the PCMCIA, the goal behind that was. Another type of PCMCIA card, express card standard for different external devices to connect to portable computers. Data transfer rates 250 megabits per second in each direction for a total of 500, and came in a couple of different sizes. So again, about the size of a credit card, something that for the most part is not that big a deal as far as portability. USB is obviously something that everybody's familiar with anymore, so that's what most people tend to focus on anymore. In a lot of cases, I don't know that you see a lot of PCMCIA slots on laptops anymore, especially not netbooks and things like that. So USBs are an option for those types of situations. You don't have you have an older netbook that has a slower network card, say 802.11b or 802.11e, and you want to go to N, you can get a USB network interface to be able to access faster data speeds. So two USB standards, USB 1.1, relatively slow, it's fine for printing and things like that, but 2.0 much faster, so if you're transferring large files, want faster access to your network, obviously that's a better standard to use. USB 3.0 in the future promises a data rate of 4.8 gigabits per second, obviously a lot faster. So you see something like that, just plugs into a standard USB port on your computer, and on the other end it's kind of hard to see, but you can see right there it's the connecting part for a standard shielded twisted pair cable, RJ45 connector. FireWire, Apple computers back in the 80s developed it. It ended up becoming standard in 95, so IEEE 1394. A lot of times you'll see it on your computer, just 1394 noted on there. Gives you pretty good transfer speeds, 400 megabits per second on traditional and 3 gigabit on newer versions. You can connect most peripheral devices, and you can connect a series of computers using FireWire cables without any type of interconnecting device, so switches, hubs, etc. I don't remember how many you can actually link together, but you can link together quite a few into a network using FireWire cables. similar to USB, connecting them like that. Most operating systems are going to support them. There's a couple of different types of firewire cables, a 6-pin and a 4-pin, and you've got a couple of examples right there. The 6-pin provides power to your device, so it really depends on the needs of your specific device. You're not going to have a choice. It's going to have a port on it for a specific type of cable. Another peripheral, external peripheral, is compact flash, and the speeds, the data transfer speeds, are not all that fast, you might notice. The idea is they don't care that they're providing you with functionality that you wouldn't otherwise have. You might have, say, for example, a phone that does not have connectivity to the internet. It has connectivity to the cellular network, but not to the internet. It's got internal storage, so you should be able to connect to a network. Or cameras are another example. Things that you want to be able to connect to the network, but don't have a built-in network interface card. You can use compact flash in some instances to be able to connect to the network, either wirelessly or via a wire. So in this case, it's a wired one. You get a compact flash card that would plug in. Usually the ones I've seen in the past normally have storage built onto them. So in the case of a camera, you can take pictures just like you normally would. It would be stored onto that compact flash card, and then you can plug up your data cable on it and pull the files off instead of having to pull the card out and find a reader for it. And then probably what almost everybody's familiar with anymore, they're built on the motherboards. There used to be a time when the network interface cards, you didn't want them built onto the motherboard. Why? They failed. The motherboards are really expensive. The more things you throw onto the motherboard, the more often you're going to have to replace the motherboard. Well, really, the quality has come a long way, and your motherboards tend to last plenty long. The various components that are built onto it tend to last plenty long, so we like the convenience of having our stuff built onto the motherboard. It's very easy. All our drivers come from one place, so it's nice and convenient, especially when they start to offer dual NICs on the motherboard. So that way, if you happen to have a NIC fail, you can always plug up to the other NIC. Advantages: save space, frees up those expansion slots for other devices that you might want to plug up. Say a tuner card or something like that, video capture card that you might want. And then you've got wireless NICs. Same thing we were kind of talking about. You've got a USB interface there, but instead of plugging in the wire to the end of it, it's doing it wirelessly. I've had a few of those. I never really cared for them. The range just isn't that good on them. I've had a wireless card like that as well. That really was pretty good. Worked very well, but it does take up an expansion slot by doing that, so that's the downside of that. And then your PCM-CIA slot that adds wireless connectivity. For the most part, there's no need for those anymore. Why? Laptops all have wireless built into them anymore. That wasn't always the case, but if you do happen to have an old laptop, and this does happen in industry quite a bit, you'll have certain applications, certain devices, manufacturing devices, that programs were written for to run a specific machine using that hardware. When you get into those situations, those people, they will spend 5 times what something is worth to get it up and going, because that's the only hardware that will work with their program. So when you run into those situations, sometimes you might have a need for an older peripheral like that. Has anybody not installed an expansion card? Okay. They talk about installing NICs. Turn the power off, plug it in, turn it back on. That's pretty much the 2-second version of what they're going through. Obviously, they want you to be smart, unplug it, ground yourself, those types of things. But don't get electrocuted, those types of things. But it's not rocket science. Just be careful. Make sure the expansion card matches. It's the same type of bus that you're plugging it into for the expansion port on the computer. There you can see one. If you haven't done it a lot, just line it up. Make sure that it's lined up well. It's not uncommon to have to provide a little bit of pressure to push it down to get it to slide in there. In fact, a little bit of pressure is probably a good thing, because that way you know it's going to make good connectivity. If the slot's too loose, you're probably going to have some connectivity issues. Once that's in, there's a screw back up there that you would screw back in to make sure that it holds in place. Usually on a network card, it's not a big deal because the RJ45 connector just kind of pops in there. But on an expansion card that has, say, for example, a video card or some type of serial connection where you're having to push in pretty hard, sometimes you can rock that back a little bit and you'll end up with a bad connection, so that can cause a problem. So you definitely want to get that screw put in. As far as PCMCIA cards, for the most part, you don't have to unplug it. Usually the operating system's just going to recognize it and you're good to go, so you can plug it in while it's on and running. As far as configuring the NIC, like I said, PCMCIA adapters, most of the time you don't have to reboot. On servers, it says other high-end power computers, you might want to install multiple NICs. If that's what you're doing, you might do that for, number one, redundant connections. If a connection goes down, you still got connectivity to that server. At the same time, you may be doing it for the benefits in terms of speed. You've got more ports to that server, you're going to be able to increase your speed to it. So you're just repeating the same process over and over again. Device drivers, that's the software that allows the operating system to be able to talk to the hardware. So it's kind of a go-between. It's going to do the little conversion of allowing those two devices to be able to talk to each other. If you purchase the computer, obviously those drivers are already installed. At least you certainly hope they work. But if you're adding hardware, you've got to install those yourself. And most of the time that just means letting Windows find it, and usually it does a pretty good job, especially today. Wasn't always the case, but today it's usually pretty good, unless you have an exotic piece of hardware. In those cases, the drivers won't be there. You'll have to provide them yourself. Built-in drivers automatically recognize the hardware and install those drivers. If they're not available from the operating system, you're going to install them yourself. Usually it's going to come on a disk with whatever you purchased it from, or you can download them from the website. Probably most of the time, if you got them on a disk, you can go ahead and install them from the disk. But the reality is you're probably better off going to the website because it's more recent. If there's any updates, things like that, they're going to be posted on the web. And that was just an example of the screen that if you had to navigate to a location where the drivers were, you can do that. Personally, I prefer to install the drivers that way. I prefer to install the drivers, generic drivers, because I don't like the bloatware that a lot of times you get on their CDs. They have their various configuration utilities and things like that just kind of clutter up your system. And that's something I try to avoid. But some people like those, and in some cases there's some additional functionality that you get in their applications that you don't get in the generic drivers. But that's up to you. That's a personal preference of mine. After the NIC is installed, test by transmitting data. Something that is useful, but certainly not necessary, are the LEDs that are on the back of them. If you've got a green flashing light, chances are pretty good it's working. If it's flashing, it's probably transmitting and receiving data. That's a good sign. If you've got LEDs back there and they're not doing anything, that's a bad sign. So as far as what the LEDs actually mean, while there are some similarities from NIC to NIC, they're not always the same for every manufacturer or for every model from each manufacturer. So that is something that's different, so you'll want to look at their documentation if you want to know what specific ones mean from each one. If you run into problems, part of the problems may be an IRQ problem. I'm not going to go into it too much, but an interrupt is basically a process that tells the central processing unit, the CPU, to say, hey, wait a minute, you need to pay attention to this particular task. So the keyboard, for example, has an IRQ number that's associated with it, so that when you hit a key on the keyboard, the CPU stops for a fraction of a second and listens to the command that you issued from the keyboard. Same thing for the mouse, the sound has it, there's several different ones. Well, in some cases you'll install a card and there'll be an IRQ conflict, and you can run into some problems when that occurs. As far as some of the common IRQ numbers and what they're associated with, they give you a list in the book. But if you've got two devices that happen to be using the same one, you've got an IRQ conflict. That can lead to a whole host of symptoms things that happen if you're sharing IRQs. And if that's the case, you have to reset one of the IRQs to one that's not being used. You can do that through the operating system, through the adapter's EEPROM configuration utility, or through your computer's CMOS configuration utility. Or if it's really an old system, jumpers. So, or in some cases, there were a few devices that use little switches on the devices. And then it talks about CMOS and BIOS and memory range. I'm not that worried about most of this, including the IRQ issues, because for the most part, your operating system takes care of all that for you now. Every now and then you may run into an issue, but it's really pretty rare anymore as far as any kind of conflicts with respect to that. Choosing the right NIC considerations, compatibility with the existing system. So your bus type. Don't buy a PCI Express network card if you don't have any PCI Express slots. It's not going to do you any good. It's going to look pretty sitting in the box, but that's it. Access method, connector types, transmission speed. So are you using token ring? Are you using Ethernet? Don't buy a token ring card if you're using an Ethernet network. Connector types. For the most part with Ethernet, we use RJ45. If there's some kind of weird thing going on, at your place and you're using some kind of weird connector type, you got to make sure you're using the same types. Drivers available. Again, for the most part, that's not a problem if you're operating in the Windows environment. If you've got a Linux box, though, make sure the drivers are available for that particular card. Linux has come a long way. They support an awful lot of drivers, or their drivers are written for an awful lot of cards now. That wasn't always the case. So, especially if you've got a weird card, make sure that there's drivers for it. Subtle differences affecting network performance and important for the server. So, differences between NICs that may be specific to your application. So they did a good chart here, I think, that kind of sums up some of the features that you might look for in a NIC, the functions and what the benefits of what some of those might be. So who knows what direct memory access is? DMA is something that came out, it's been around a long time, but it was an attempt to start to relieve the CPU of some of the management functions that these various peripherals have to go through. So before DMA, if a device needed to access memory, it had to go to the CPU and say, hey, I need to access this part of memory. So the processor would have to stop what it was doing and address that request. If it wanted to write information to memory, it would stop the processor, write it to memory, and the processor would have to stop and help with that process. DMA allows those peripheral devices, those expansion devices, to be able to directly access memory itself, freeing up the processor to continue to work on whatever it's working on. So it's a way for the device itself to directly access memory. And that helps to improve performance significantly. It's something we take for granted today, but it wasn't always the case. So it definitely improves performance. Those LEDs, again, they're different from card to card, but it's nice to be able to have LEDs just to know that, hey, something's working. It's getting power, the lights are flashing, so it's transmitting, it's receiving. It looks like it's working okay. That gives you a lot more information than no LEDs, and so now you don't know anything about the functioning of that particular network card. So that's a nice thing to have. Some network cards have power management capabilities, probably more important on laptop computers. If you're not connected to the network, have that network card automatically power down. Why? It saves battery life. Network cards sending and receiving on the network consumes battery life. And then there's a number of other things that I'll let you guys look through. Okay, so we've got those network cards into our computers. They're configured, they're functioning, everything's working fine. On the other end of that cable, or the other end of that wireless connection, they've got to connect to something. And in this case, it would be on the other end of the wires, repeaters and hubs. They're essentially the same thing. The distinction is the number of ports that they have. A repeater is just going to have 2 ports. It's a way to tie in together 2 different segments, if you will. So it's the simplest connectivity device regenerating signals, operates at the physical layer, has no means to interpret data. So it's not opening up any of the frame at layer 2. All it's doing is getting in those literal ones and zeros, or those, not even the ones and zeros. It's getting in those electrical pulses and sending them back out on the other side. It is regenerating them, so it's cleaning up the signal if the distance is pretty long and started to deteriorate, so that's good. But it only has that one input and one output port. Suitable for bus topology networks, allows you to extend that network really pretty cheaply. I've never seen one of these, and I bet you've never seen one of these. I'm just going to go out on that.
The repeater?
Yeah, just a repeater.
We use them in the Cisco labs.
Wow, cool. Limitations, other devices, decreasing cost. What's that mean? That means switches are do a lot more, and they cost very little. So why would you use something like that? A hub, like I said, is basically an extension of a repeater. It's got more ports, but it does basically the exact same stuff. Multiple data ports and an uplink port, repeats the signal in broadcast fashion. That broadcast fashion is the limitation of hubs. It's why they're unsuitable in a modern network, especially a network where you're passing video on, or large files and things like that. It's just that it's not suitable in a broadcast network. Operates at the physical layer, just like a repeater does. An Ethernet network hubs can be a star or star-based hybrid central connection point. Connects workstations, printers, switches, files. It may look physically exactly like a switch, unless there's wording on the device itself, or you look up that device itself. You may not know whether or not it's a switch or a hub, because physically cables plug up to it just like they would a switch. But the functionality that's occurring inside of it is significantly different. Devices share the same bandwidth amount and the same collision domain. So the more nodes that we connect to it, the more computers, etc., that we plug up to it, the likelihood of those collisions goes way up. The more collisions we have, the more often we have to retransmit lost data packets. The problem just gets worse and worse. Placement in networks varies. The simplest standalone workgroup hub. Very simple network. You've got a few computers. You stick it in the middle and connect all the computers to it. You can also have a different hub to each small work group. Placement must adhere to the maximum segment and length limitations. So again, you can only have so many connection points, so much length between a hub and its various nodes that are connected to it. So no more than 100 meters, 100 meters, 100 meters. 1, 2, 3, 4. I got too many here. So they may run into connectivity problems from the nodes over here, trying to connect to nodes over here. A very simple hub. It looks something like that. On the back, looks like that's probably an 8-port. Probably an 8-port hub. In the back, just plugs right up. Passive hubs, intelligent hubs, or managed hubs. In some cases, managed hubs, you would have the option to be able to retrieve information about how that hub is performing, how much data is going through it, things like that. But again, you're just not going to see these in use that much anymore. It's replaced by switches and routers because of the lack of features and the signals have to be repeated. Bridges connect two network segments. Analyzes incoming frames to decide where to send based on a frame's MAC address. So this is kind of the next step forward. It's not quite, it's kind of like a hub, or excuse me, it's kind of like a repeater, but it's operating at layer 2. It's opening up the packet, or the frame, to look at the MAC address and learn a little bit about that packet, or a little bit about that frame. So it operates at the data link layer, has a single input port and a single output port. So that's how it's like a repeater. It's not like a repeater in that it operates at layer 2. It interprets that physical addressing information, and then that's what allows it to determine which side, which port that information should be sent to. It's protocol independent. It adds length beyond the maximum segment length, so you can extend the distance between nodes on each side. and you can improve network performance because what you're doing is you're reducing your collision domain. So if you've got a bridge that looks something like this, if you've got computer 1 over here attached to a hub, these 3 computers, 1, 2, and 3, are all in the same collision domain. If 1 sends a message to 2 at the same time that 3 sends a message anywhere, there's going to be a collision if it occurs exactly at the same time. The advantage to a bridge, though, is it doesn't include 4, 5, and 6. The bridge, the information comes out to the hub looks at it and says, you know what, that MAC address that you sent it to is on this side. I don't need to rebroadcast it over here, so I'm just going to drop that packet. If it needs to contact 6, it sends it to these computers as well, but also to the bridge. The bridge says, wait a minute, according to my database, that particular computer is not on your side, so instead of discarding that frame, it forwards that frame over to this hub, which then broadcasts it out. So it allows you to segment your collision domain in 2, and as a result, you end up with fewer collisions. You still have the possibility of collisions because you've still got a number of nodes connected to each side, but you've reduced the likelihood of collisions because you've segmented the network into 2. As far as how it goes about learning those different MAC addresses, it does it slowly over time. As you send out more and more packets from the various nodes, it creates a database inside that bridge. That bridge then, over time, identifies each node and its MAC address, and that's how it associates which port to discard packets from or frames from versus which ones to forward to the other side. Again, bridges are nearly extinct. You're not going to see them because switches are cheap. So a switch is to a hub like a bridge is to the repeater. So you've got multiple ports. The difference is they all act like an individual bridge. So you all but eliminate the issue of collisions. The reason you don't completely eliminate collisions is you still have certain protocols that send out broadcast messages. And that's necessary for certain network functions. So you don't completely eliminate collisions, but you certainly can curtail them significantly. Switches operate at layer 2. They're supposed to traditionally. You do occasionally hear about layer 3 or layer 4, even layer 7 switches. If you ask me, a switch is layer 2 and everything else is other stuff. Layer 3 is not a switch, it's a router. But you will certainly see different manufacturers market them as a layer 3 switch or whatever. So be aware that just because they're calling it a layer 3 switch doesn't make it a layer 3 switch. It may be just their marketing terminology. So switch, like I said, operates at layer 2, so it interprets a MAC address. The components of a switch, it's more intelligent than a hub is. So it has an internal processor, an operating system, simplistic as it may be, but an operating system, memory, and then a number of ports, usually at least 4, and I think the biggest one I've seen is probably 24 ports on a single switch. But you can combine them together to come up with an awful lot of ports. So a relatively cheap switch on the right, and then much more complex one on the left. I think the book's actually labeled wrong. It says something about this one being a 24-port switch, and it looks like 8-port to me. Multi-port switch advantages over a bridge. Better bandwidth use, more cost efficient. Why? You buy one switch instead of 8 bridges. Each device effectively receives its own dedicated channel. That's what eliminates or significantly reduces all those collisions. From an Ethernet perspective, the dedicated channel represents the collision domain. So because it's each individual channel, you just really reduce that likelihood. For the most part, we want to replace hubs with switches. It eases congestion. We're not going to have all those collisions that occur. Provides better security because with a hub, we're broadcasting out that information whenever we send out a packet. You send an email, you're broadcasting that information. Well, if you include your Social Security number, for example, on an email that's connected to a hub, email is not encrypted unless you've got some kind of add-on application that encrypts it. So if you're sending that across an email, anybody that happens to be on that hub can listen into your connection. That's the same issue with cable modems. It's the same type of shared environment. So anybody that happens to be on that same segment can listen into your data. So be careful doing stuff like that. A switch significantly reduces that because it's a direct connection between your node and the switch, and the switch wherever it's supposed to go from there. It's not being broadcast to all the various other nodes that happen to be on that network. Disadvantages: switch can become overwhelmed, especially if it's getting used a lot. If there's a lot of people using it, that switch can really start to develop problems in being able to address all the various requests that are being sent to it. So it can start to drop packets occasionally if it's being utilized an awful lot. Switches replace workgroup hubs because of decreased cost, easy installation configuration. On cheap switches, there is no configuration. Plug it up and go. And they can separate traffic according to port with a virtual LAN. Installing a switch, I mean, it's not rocket science for the cheap ones. They're really pretty easy. The managed ones get a little bit more complex to be able to set up. But general steps: verify wherever it is you're physically going to place it. Verify lights and self-power tests. Turn on the switch, verify those lights. Configure it if necessary if it's a managed switch. Connect NIC to a switch port. Repeat for all the other nodes. After all the nodes are connected, connect them and try testing some communication. Start pinging something. So it might look something like that. Switching methods, differences in switches, incoming frame interpretation or frame forwarding decisions to make. So 4 switching modes exist. 2 basic methods are discussed: cut-through mode and a store and forward mode. And it's just how does the switch go about processing packets as they come in, or frames as they come in. Cut-through is probably the most efficient in terms of speed. All it does is as it receives, let's go back to the frame that we talked about earlier. And again, I told you you didn't have to know the entire frame, how it's laid out and all that kind of stuff. But if you remember at the very beginning of that frame, it had address information. Where that frame is coming from, where that frame is going to. The cut-through mode approach, what it does is as that frame is coming in, it's reading that information. And it says, oh, destination address. And it sends it directly to the port that it needs to go to reach its destination. It doesn't bother to wait for the rest of that frame to come in. It just starts transmitting. That's fine until you get to the very end where you do some error checking and you find out, oh, wait a minute, there's an error with that frame. With cut-through approach, it doesn't matter. It's already sent that frame. So on the receiving end, it says, oh, there's a problem, we have to resend that frame. So you're broadcasting data, potentially, that is bad data, and the switch could have caught it, potentially. But it doesn't because you've started broadcasting it immediately as it came in. So for smaller networks, it can definitely speed things up. Networks where you're not going to have a lot of problems. But, and you can actually detect some errors. There's just other errors that you can't detect. So it's not a real good approach in a really busy network. Part of the advantage is also part of the disadvantage. By doing it the way that it doesn't have to have any additional memory in that switch. Why? Because it's just processing it. It's not storing it. It's just shipping it right through the switch. So it's not buffering any of that information. So that's why it doesn't work as well on larger networks. It doesn't have that memory. So as the network becomes more congested, it's going to start to drop more frames because it can't process them. It doesn't have any memory to be able to store those frames. Store and forward approach, however, does have additional memory built into it. It takes that packet in and analyzes it first. And says, okay, look, this looks like a good frame. It's passed the error check. We're going to go ahead and forward it to the port. But it has to have enough memory to be able to store those frames. Best use, it's more time consuming because it's taking that entire frame in before it starts to transmit it. And it's fine for larger environments or mixed environments. Can transfer data between segments running different transmission speeds. So if you're on a network that has 10 meg cards as well as 100 meg cards, you can mix and match those. This is what's going to allow you to do that. Okay. Anybody played with virtual LANs? Are they difficult at all?
They can be kind of confusing, especially if you get it mixed in with like an ACL. It kind of gets hairy.
Keeping track of which nodes are connected to which virtual LAN?
Yeah.
Because they all physically look like they're together. Virtual LANs are a way to logically break up your segments on your network. And I think you kind of hit the nail on the head. It can be, documentation becomes very important because physically it looks like you've got a switch and you've got all your various nodes plugged into the various ports on your switch. So physically it looks like these various switches or these various nodes are all part of the same segment. Logically, through the managed portion of the switch, however, you've designated, say, ports 1, 2, 3, and 4 to be on a virtual LAN. 5, 6, 7, and 8 to be on a different virtual LAN. Why would you want to do that? Well, you may want to break up a broadcast domain, for example. You may want to have one particular segment where you have faculty information or faculty share files and things of that nature, but you want to have a completely different segment for students to be able to access. So you want to be able to separate that data so that there's no security concerns with the two being mixed. And that's the purpose behind a virtual LAN, is to be able to segment your network logically rather than having to have a separate switch, separate routers, and all those various types of devices to be able to physically do it. So I know it's hard to see there, but it kind of highlights different computers that are connected. Now, if you look physically at this switch 1, you've got nodes here, a node here connected, a node here connected, a node here connected. But you've also gone switch 2, got this node connected to this node connected to this switch. But they're all part of the same virtual LAN. So they can physically be connected to different physical devices, but they're considered to be on the same segment because of the way that the virtual LAN has been configured. Advantages: flexible ports from multiple switches or segments, use any node type. Reasons for using virtual LANs: separating user groups, isolating connections, identifying priority device groups, grouping legacy protocol devices if you want to pull certain protocols off of the main part of the network and isolate them. As far as creating them, usually through some kind of software, mainly through a configuration utility, or in a lot of cases a web browser. There'll be a web server that's built into the virtual LAN device, and you'll access it through a web browser in a lot of cases. Critical step: indicate to which virtual LAN each port belongs. This is what we were talking about a minute ago. Again, you've got 24 ports, say, on a switch. You've got to keep track of physically port 1, port 2, port 3, and what virtual LAN that port is associated with. It can kind of get mind-boggling if your documentation is not real good. Additional specifications, security parameters, filtering instructions, port performance requirements. As a managed switch, it should be able to provide you with a lot of that information. How is your network performing? And you should be able to get a lot of that. Some of it, in terms of which switch that you purchase, may be dependent on the type of information that it can make available to you. If you really want a lot of performance information back, you probably want to look at the performance information that switch is capable of providing before you make that purchase. So there's a configuration file or information back from a Cisco switch telling you, for example, which ports are associated with which virtual LAN. VLANs and trunking. Potential VLAN issues: cutting off a group from the rest of the network. Even though physically they're connected, because it's a virtual LAN, it's treated like a separate physical LAN. You address that, since they're basically different physical LANs, you've got to connect those different LANs together just like you would any other different physical LANs. So you end up using a router to be able to do that. Another type or another approach that you could potentially use is through trunking, allowing the switch's interface to carry traffic from multiple virtual LANs. So a single port doesn't necessarily have to be isolated to one and only one virtual LAN. So trunk is a single physical connection between devices. Many logical VLANs transmit and receive data. As far as virtual LANs, the way it actually occurs with the packet that goes, or the frame that goes through, part of the frame contains a VLAN identifier. Each frame that goes through has a number associated with the virtual LAN that it's associated with, that frame's associated with. That's what allows the virtual LAN or the switch to be able to identify that this frame is associated with this virtual LAN, and that a different frame with a different VLAN number is associated with a different virtual LAN. Advantages of VLAN trunking: economical interface usage. Switches make efficient use of processing capabilities. So what we were talking about, it's not necessarily the easiest thing to configure, and really requires a lot of good documentation, keeping track of what nodes are plugged into which ports and which VLANs you need associated with, or else you're going to end up investing quite a bit of money in routers as well. STP, spanning tree protocol, operates at the data link layer and prevents traffic loops. There's occasions where you want to start to interconnect various switches across your network in an effort to build in some redundancy, to allow parts of the network to have a problem, yet at the same time that creates a problem that STP is actually designed to prevent. You can create those broadcast storms that we were talking about earlier in a switched environment if it weren't for this. Let me kind of skip forward because I think it kind of illustrates it a little bit better. So in this particular case, you've got redundant connections. You know, you've kind of got a loop right here, you've got a loop here, you've got a loop here. So if we're trying to connect between devices, which route should it take? Well, when it broadcasts over, if it doesn't know the actual MAC address of where it's trying, or the actual address of where it's trying to send a particular packet, it's going to broadcast at layer 2 to switch B, for example. Well, switch B doesn't know either. It's going to broadcast it to switch E. Switch E is going to broadcast it to switch D, and in turn, it's going to broadcast it back to switch A. You run into this problem of creating a broadcast storm in your own network by doing something like that. STP allows intelligent decisions to be made for devices as those broadcasts are occurring. So instead of sending it out every route, in this case it might send it this way, this way, this way, and this way. So switch F gets it, switch E gets it, so you can identify the specific node that a message is being sent to. So what happens if all of a sudden this network connection goes down? STP should automatically at that point recalculate and say, I want to open up this one, or I want to open up this one. I want to open up both of them. It'll open up one of those in order to be able to reach the rest of the switches on the network. It's a way to be able to have that redundancy, yet at the same time not cause those types of issues where you're constantly hitting, get caught in that recursive loop. Originated back in the 80s. It's not particularly efficient, the original version. RSTP, a newer version. Cisco has their own version if you're using only Cisco switches. If you're using other switches, it doesn't work, but Cisco has their own proprietary version. It's included in the operating system software. You don't have to worry about it. Switches automatically take care of that for you, so it's not the type of thing that you have to set up and configure. Content and multi-layer switches. Switches operating at layer 3. Now, again, I would contend that in the purest sense, there's not a layer 3 switch. It's a router, but there is certainly things that are marketed that way. So there's a lot of gray area as you go from one layer to the next in the functionality that's provided. Advantages of these higher layer switches is they provide advanced filtering, better statistics, more statistics, for example, security functions, things like that. So there's a lot of functionality that's built into them the higher the layer that you go up to, because you have a lot more granularity that you can control below those layers. But again, to me, a switch is a switch, a router is a router. Content multi-layer switches, disadvantages. No agreed upon standard. So like I said, just because Cisco calls it a layer 3 switch does not mean that 3Com calls it a layer 3 switch. There's no standard. Distinguishing between layer 3 and layer 4 switches, it depends on the manufacturer. If they can convince you that it is a layer 3 or layer 4 switch or higher, a lot of times they can get you to pay more money. If you're a philanthropist, that's great for you, but I would try to spend less money if I could. So if switches are smart hubs, routers are smart switches. Routers operate at the next layer, layer 3 of our OSI model. Directs data between network nodes, integrates LANs and WANs. So this is what allows us to connect different networks together. Which operate at different transmission speeds and protocols. Directs data from one segment to or network to another. Uses logical addressing. What are we talking about with logical addressing? IP address. I mean, there are other ones obviously, but that's in our world, for the most part, that's our IP addressing. That's something we set. The MAC address at layer 2 is a physical address. For the most part, we don't set that. There are exceptions, but for the most part, we get it from the network card from the manufacturer. It's set. That's what we go with. That's a physical address, versus the logical address is our IP address. Routers at this layer, protocol dependent. Slower than switches and bridges. Why?
It has to make decisions.
It's got to make decisions. It's got to go further into our information to be able to determine where it's going. Whereas the frame at layer 2 only had to open up the next layer up, we've got to go 2 layers up to get to layer 3 to be able to look at that IP address and say, is this the right node, or do we need to send it to the next router? So it takes more time to process. So when we can avoid switches, or excuse me, when we can avoid routers, we want to do that. We'd rather use a switch whenever we can. They're more efficient. But obviously, at certain points in our network, we have to have a router, especially when we're trying to connect our LAN to the internet. Traditional standalone routers, LAN routers, being replaced by layer 3 grounding switches. I don't know about that. It's the same thing. New niche, specialized applications, linking large internet nodes. Router characteristics and functions. Intelligence tracks the node location, determines the shortest, fastest path between nodes. That's the router's function. It's got to figure out how to get this packet from point A to point B. Shortest, quickest. We'll talk about this here in just a little bit when we get to routing. The best path is a difficult term to define, because shortest path is not necessarily the best path. It can be, but it's not always. Large LANs and WANs, you have to have routers, because routers are what allow you to break up networks really pretty easily. Router components have an internal processor, usually a more complex operating system than a switch would have. Memory, input and output jacks, management control interface. A lot of times they'll have a web interface to be able to log into the router and configure it. Depending on the complexity of the router, you either have little or an awful lot of control over what router functions that router performs. So a little bitty cheap Netgear router, a little more intermediate, and a very complex router on the very left, far left. Really cheap, really expensive. So what are the tasks of the router? Connect to similar networks. Maybe you're connecting a TCP/IP network to a dissimilar network, something that's running IPX, SPX, or something like that. Interpret layer 3 addressing, determine the best data path, and reroute traffic. Optional functions are things like filtering broadcast transmissions, enabling custom segregation security, support simultaneous connectivity, provide fault tolerance, and monitor network traffic and diagnose problems. This is what I was talking about earlier. When you log into that router, how much control, how many features that particular router has is going to give you different types of information. In some cases, you can run diagnostics from your web interface into the router. There's a lot of information you can get back. In other cases, especially if you go with something like that, you're going to get very limited information back. It's not going to be able to do an awful lot of diagnostics for you. router characteristics and functions continued. Static routing and dynamic routing. For the most part, you want to avoid static routing. Why? If you have a connection that goes down, data is not going to get through, period, because that's a static route. It's just not going to change. Dynamic routing automatically adjusts as connections come online, as connections go off. It's going to automatically adjust for you. It's much easier to manage, and it's more responsive. Installation of routers can be very simple if it's a real basic one, to something that's very complex if it's a real large system, especially if you're configuring some static routes. So you might look something like that, and again, a router is designed to facilitate communications between different parts of your network and other parts of the network. And on a small network, again, that's pretty easy to do with a basic router. As the network grows larger and larger and requires more configuration, it can get pretty complex pretty quickly. Routing protocols. We've got to figure out the best path to get from node 1 to node 2 or node A to node B. Best path defined as the most efficient route from one node to another. Most efficient route usually is going to be the quickest, but that's not necessarily the fewest hops. Hop is from one router to the next, ultimately until it gets to its destination. So it's dependent on the number of hops, current network activity, so how busy is the network. So even though it may be fewer hops, if the network's really busy, our information, our packets may not be getting through as quickly as they otherwise would. Links that go down, network transmission speeds, and topology. So our routing protocols are going to make some of these decisions for us. Routing protocols is how routers communicate with each other. So it's not the decision, it's not the protocol that we're using on the internet like TCP/IP, though some routing protocols kind of piggyback on that. It's the actual protocol that the router uses to make decisions about how a packet is to be directed across the network. So it collects, a routing protocol will collect current network status data, various links. Are they up and running? How are they functioning? Contribute to the best path selection, and creates a routing table that it keeps track of. These links are working, these aren't, etc. The issue of router convergence refers to the fact that those links change over time. You know, somebody unplugs a switch or a router to let it reset. Well, obviously those connections go down for a period of time. AT&T cuts through a data line at some point. That's going to cause some of those connections to go down. So the router convergence time is how long does it take for it to identify accurately those various links, the ones that are up and running versus those that aren't. Distinguishing feature between routers, overhead, the burden on network to support the routing protocol. Again, with dynamic routing, it's much easier to reduce some of that workload on your support staff. So in general, this book talks about a couple of different classes of routing. They talk about distance vector routing and link state routing. Distance vector determines the best route based on distance to the destination. Distance, number of hops. So factors include hops, latency, network traffic conditions, etc. RIP is a real popular distance vector routing protocol. Only factors in a number of hops between nodes, and it's limited to 15. So that's a problem in the current design of the internet, that is as large as the internet is now. That's a problem. It's one of the, I think it's one of the very early routing protocols, so you really don't see it used, but it's referred to as an interior routing protocol, slow and less secure. So because of some of its limitations, you end up with version 2, but it still has issues because it's limited to 15 hops. So it also does not tend to be used. Border gateway protocol is much more common, communicates using border gateway protocol specific messages. Uses a lot of factors to determine the best paths, and it's configurable to follow policies. So you may have certain messages that you want to take a particular path. You can create those and have those policies followed. But it tends to be more complex. It's more difficult to set up. Link state, you We've got a couple of different standards. There's a lot more, but these are the ones that the book talks about. Open shortest path first and ISIS. In link state, routers share information. They do that by periodically polling each other and saying, here are my links, this is the status of my links, how are your links? And they compare notes. Well, the downside to that is that takes up bandwidth. That takes time for them to be able to share that information. To make sure they have accurate information, they have to do that regularly. The more regularly they do that, the more bandwidth they're tying up just in that routing information. Open shortest path first is one of those protocols. It can be an interior or border router use. It does not have a hop limit, so that's a big plus. Uses a complex algorithm for determining best paths. Each open shortest path first router maintains a database containing other routers' links. ISIS, for interior routers only. If you go through the book, it talks about interior routers, gateway routers, and exterior routers. These are ones that are internal to you as a company, ones that sit between you and the internet, and then those that are out on the internet that are away from you. Interior routers only supports layer 2, supports 2 layer 3 protocols, IP and ISO specific protocol. It's less common than open shortest path first. And then hybrid EIGRP. Link state and distance vector characteristics. So it kind of shares some of the characteristics between the two. Cisco network routers only. Fast convergence time. So it reconciles the differences between the actual state of the various routers that are available on the internet and what it thinks is available. Low network overhead. Remember, sharing that information with some of the other protocols created additional network overhead. This helps to reduce some of that. Easier to configure and less CPU intensive than open shortest path first. Supports multiple protocols and accommodates very large heterogeneous networks. So networks from different organizations, completely different configurations. Gateways and other multifunction devices. Gateways are kind of a catch-all term for a lot of different types of devices. From a web perspective, a gateway is oftentimes the same thing as a gateway router. It's a default location where you send a web request to be forwarded up the chain of command or up the DNS server command, if you will, finding that address. It's not a local address. Send it to the gateway will go find it. But it can mean other things depending on the context in which it's used. Combinations of networking hardware and software connecting two dissimilar networks. You can connect two systems using different formatting, communications protocol, architectures, etc. So popular gateways, email gateways, internet gateways, which is what I was just talking about, a LAN gateway, voice data, firewall, etc. So this chapter, we talked about network interface cards, the different types of network cards, whether they're internal or external, the different types of buses that they might plug into. Then we moved on to repeaters and hubs and talked about you're not going to see those anymore. They're not practical with switches and routers. Talked about bridges as well. Switches, we talked about some of the different types of switches, and we also talked about some of the routing characteristics and functions, some of those protocols, and how messages get from point A to point B through various hops and things like that. And then here just a second ago we talked about gateways and stuff. So, any questions over that?